Hello everyone, today we're going to talk about the Newton's law, all three. Firstly, we're going to talk about the first law, one part of the first law, because there are two. An object at rest will remain at rest unless acted on by a force. So let's say an example, let's say there's like a box on a surface and the box has a mass of 10 kilogram. So there's no forces, it's at rest. So the only forces that are acting on the box are the weight and the normal force. So the weight equals to mass times gravity. So that will be 10 times 9.81. So the weight, so the force for the weight is 98.1, and because it's still it's not falling down or anything, because of the normal force, it's pushing it up in a way so it stays there. I don't know how to explain it, but that's I'm pretty sure I did already explain that in the last videos. So I recommend you guys to watch all my videos because, of course, all this knowledge, it's not mine. I revise myself, I watch videos, and then I just yap what I heard to you. So, of course, this is not mine. All this work is not mine. That's just the truth. However, I believe that my explanations, they're more kind of close to students in the way, if I don't understand it, why would you understand it? So I only say if I understand it. So you probably learn more from my videos, I guess. However, that's beside the point. Back to locking in. Basically, remember, the atoms here, they're pushing the box up so it doesn't actually fall down because of the gravity pulling it down, the weight. So the normal force is the same, which means that this whole thing, it's balanced, and the net force equals to 0, which means it remains at rest unless we will just apply an unbalanced force. Only then the box will start moving. So basically, the first part of the first law says that if it was at rest, it will be at rest, in basic words. Now, what about the second part? So basically, the second part says that an object in motion will continue in motion, will continue to be in motion unless acted on by a net force. So it's kind of the same as the first part, however, kind of the opposite. It's not at rest, it's actually moving this time. So let's say we have a surface, right? It's a rough surface, let's say don't know, a carpet. If let's say you're trying to roll a ball, right? It's moving, but it will really quickly come to a stop. You pushed it, right? And it's moving, but it will be for a very short period of time. And the reason for that is, even though it's in motion, because of the friction, there's too much friction between the surface of the ball and the carpet, and friction opposes motion. Basically, it's the opposite of motion. Friction and motion, they're top one enemies, right? Because motion is moving and friction tells it to stop. And because there is a net force, in general, because there is a net force in this type of situation, that means the object will not continue in motion. It's not never ending, let's say. I mean, that is quite logical, however, not at the same time. So, however, the first law, the second part says that if it is in motion, it will continue to be in motion, if there's no net force, which is technically a brother to the friction. Now, what do you think what would happen if we could just get rid of the friction? Done, it's not there. Will it continue moving forever, or what? Now, imagine you have a smooth surface, right? Let's say it's ice. I'll make it blue for it. And let's say we just take a puck. In case you don't know, a puck is the thing where the guys with the tennis rackets play on ice. I think that should be a good example, because I personally didn't know what's the point, but that's a different story. Let's look in. and like let's say we slide it across the ice, right? It's going to move like for a very like large distance, right? Like it's not going to be like at rest like the ball on the carpet. They're two different scenarios. Like this one will go like far. Now how about like kind of forget about the punk. Let's say we use the ball, like again, like the ball as example. Now this time it's going to roll for a very long time. Not because like the thing is, you have to understand, it's not about the object, like the puck, it was just a good example, because like ice and pucks, they manage. However, it doesn't matter, it's all about the surface. Like, if it's flat, if it has a low friction, then whatever you put there is going to go forever. I can put a brush, a literal hairbrush, and it's going to be similar to the ball and puck situation. The only difference might be because of the form of the object. Like, if it's uncomfortable, like the object can be kind of friction itself, because let's say, the hairbrush, it has these tingly things if you put it, like, to the way. So you just have to understand, like, friction, it can be also an object, kind of, at the same time. However, it's most of the time, like in engineering, let's speak properly, it's on the surface. So if you're still confused, like why these two, like what's the difference between like why does it matter if it's on ice? Like why does this one go for a long time and this one for a very short period of time? The reason for that is because again friction, guys. There's way more friction between the carpet and the ball because like the carpet's they're rough, so the ball has to like kind of like bump, like go up, go down, and like maybe like down, up. It's about the friction. And the ice has much more less friction. Of course, ice can have holes. However, you know when you ice skate, like imagine you just come in the morning ice skating and it is smooth. It's like, it was just like, or what was it called? It was just like polished. That's what we're talking about. Literally no friction. That's also why it's like so like easy to like kind of fall down, like crash your head and whatever. Now let's think about it a bit more deeper. What if we literally completely get rid of friction? Like, even though the icy surface has basically no resistance, don't forget there's air resistance. Like, all these earth stuff, like, in general, the earth, like, the air, that is still friction. Because, like, let's say you're just, like, waving your hand, I'm waving my hand right now. I can feel, like, the air. Because the air is still a part of, like, it's an invisible wall that's extremely soft. That's kind of, think about it. So the place where there's no literally like 0.0000001% of friction, probably even less, is the space. So as a good example, so we know that the Earth evolves around the sun, right? And it was evolving for it like very long time, like, and it is still moving, guys. Literally right now you're watching this video, it is moving. And that does make sense because in the space there's literally no pressure for, like, there's nothing to stop it, like there's no air resistance. And that is the first, like the second law of action. If it's in motion, it will be in motion. If an object remains at rest, the net force acted on the object is equal to 0. So if something is at rest, the net force is equal to 0. So if it is at rest already, then it's equal to 0. No, like the box, it stands still unless I like do something to it. Whilst that's still, the net force is equal to 0. So you have to understand that. So the other thing is, like, let's say there's an object and it's moving at constant velocity. Also in this case, the net force is equal to 0. The reason for that is, so in general the net force is like, let's say again the box is moving, right? And that it already has kind of a net force of like all these added bits. So let's say it's just moving like with the gravity one, the normal one, and the 10 newtons. Adding kind of these all up or whatsoever, like all of this together is equal to 0. However, if there is friction, another force adds, which is the resultant velocity. It adds up, like even though it's a minus, it like adds up to all this thing and it stops being a 0. So, remember, if the net force is 0, whilst constant velocity, that means that also the acceleration net force is also equal to 0, because acceleration is basically like how like the speed, like adding speed. If it's constant, there's no speed adding, so there's also no acceleration happening. You have to understand that acceleration equals the final velocity to equate the initial the velocity. So like the change in velocity divided by the change in time. So this is the final velocity, and then the initial. So basically the final velocity kind of means what was before, if that makes sense. So if like at constant velocity, again constant velocity, that means that both the like velocities are the same. They're like, let's just say 2. They're both 2 because it is constant. It was constant. It started at 2 and it is going at a 2. And like when you take away, for example, 2 times take away 2 is 0. And 0 over t, like just, we could add the number, but like, so the second law states that the net force is equal to the product of the mass and the acceleration. So the mass and acceleration. So basically what it says is that the net force equals mass times acceleration. Now let's talk about like the theory itself, right? Let's say the acceleration is constant, like it doesn't change, right? However, if we increase the mass, the net force will increase. So the net force is proportional to the mass. Now let's say the mass is constant and you increase the magnitude of the acceleration, and the magnitude, the word like the net force will also increase as well. So the net force is also proportional to that acceleration. Now let's say we keep the net force now constant, like kind of it froze, right? Like then it's, that's how it is, right? What is the like relationship between these mass and acceleration? So let's say I increase the mass, right? Acceleration will decrease. However, that's if the force is the same. Like let's say if the force doesn't change, it works that way. So like let's say a box, right, is moving with like it's going quickly, so like the acceleration is very quick. It's like, I don't know, 10 miles per, like, and right now it's a kilogram, right? So like the force that's making it go 10 miles per hour is like, let's see, I don't know, 100 newtons, right? However, if we increase mass, like instead of it being 1, we make it 10 kilogram, that changes everything because like there's more force going down, so it creates its own friction. Like it's like, because like the force is the same, like it's harder to push something more harder. Like you can, let's say you yourself, it's easy for you to push someone who is skinny than someone who has more weight on, because like more mass equals like harder to push. That's kind of the logic. However, if you decrease the mass, that logically the acceleration will increase, because there's, sorry, I'm trying to do a video here. Okay, let's continue. So now because the mass decreased, it's easier to push. So like let's say it's now, I don't know, like 100 grams. It is much more easier to push because of the less like gravity weight pulling it down. But remember, that's only if the force is the same. So like let's say if the force changes to like, it will be much more different, because like it will have a different, it will just be different. Let's say you double the mass and the acceleration is constant, right? What effect will it have on the force? So like we doubled it, so it's to like, right now let's just think of it as all being 1s and the acceleration is 1. So the force will increase by a factor of 2. If we triple the mass, keep the acceleration constant, the net, like the force will triple too. If we triple the mass and double the acceleration, then the net force will increase by 6. Basically, the second law says that the net force is equal to the mass times the acceleration, as we can see here. Now remember how we said that the acceleration is equal to the change in velocity. So like the change in velocity, so like the v final minus the v initial, that's basically as delta v. This triangle in engineering, it represents change, so just remember like this is the same thing as this, because this is like acceleration, so it's also equal to the net force. So this is exactly the same as the V final minus V initial over change in T. Now, what is the mass times the velocity? So they're right together. So what do they even mean? So mass times velocity equals momentum. Momentum is represented by a small p. Momentum itself, it is mass in motion. So let's say an object that's at rest has zero momentum. That's how it is. Because of its like motion means like kind of moving, right? Like in movement, that means that something at rest is zero with like momentum. Momentum. However, if an object is moving, it will have momentum. Now, here's the tricky part where you kind of have to think. Let's say I have a car that's going 30 miles per hour and I have a train that's going the same as the car, 30 miles per hour. Which one has more momentum? The answer is the train. So, kind of the way to think about it, if both objects move at the same speed, the one that has more mass has more momentum. So the answer would be the train. Because as you remember, like momentum, it's not only about the velocity, it's not only about the speed, it's also about the mass. Kind of think about it like that. It's much more harder to stop the train, like with any like either friction or like a box just right here. Like yes, it will crash and all that, but it depends about the weight of the box. Like it might just like, just take it with it, like just you're coming with me. And with the car, it takes much more less effort to stop the car, much more less friction or just in general power. So kind of think about the momentum and the way how hard it is to stop it, and that's why mass also is important, because like the more mass there is on speed, like speed and mass together combined, like basically momentum again, guys, it's a product of mass and velocity. So if the object has a lot of mass and velocity, it has a lot of momentum. So if mv equals p, that means the change delta mv equals the delta p, like changing basically over here changing momentum. I mean, as if like that's not momentum, but like because it's equal to, I'll just call momentum. They both have to change, and because they're equal, it's okay. So technically speaking, you see how we have these two like already here. You just have to times it. Right now it's not times. However, if you times it, it will be there. Somewhere here. That means it's equal to this. So we're able to just write change in momentum over time. This is like another part of the second law, another one kind of. So the net force is change in momentum divided by change in time. Also, just another quick important kind of equation, I guess. Let's say you start off like there's a question like it or whatever. Let's say you start with this equation. If needed, you're able to times everything by the change of t, and so the force multiplied by the change in time will be equal to the mass times change of velocity. So these two, they're also equal. The term for the force times change of t is impulse, and the term for this, as we just known, is momentum. So the impulse is equal to the change in momentum. So the third law now, and it states that for every action there is an equal and opposite reaction. So basically, we're able to say that FA is equal to, I don't know, like F minus FB. So if you apply a force, then there's going to be a reaction force applied to you. Both forces will have the same magnitude. However, the direction will be different to each other. So basically, both forces, they will have, like the same magnitude, but direction of the, like, it will be different. They will be opposite to each other. So as an example, let's say a person jumped in the air, right? And like he didn't force, or like he's just very fast at doing stuff. And while he was in the air, right? He threw a ball, right? A tennis ball. And the force that he applied to it, let's say it is 200 newtons, yeah? And the ball is like 2 kilogram. And let's say, by the way, the person is 100 kilogram. So him applying the 200 newtons to the ball, right? So it just flies somewhere. There is this kind of resistible because of the air, because of all this stuff. Like he's kind of himself, he's like pushing away from the ball. Because like imagine you have a ball in your hands, right? And you throw it, right? You throw it. Even though you're pushing it forward, when you throw it at the end with your fingers, you kind of push it away from yourself or whatever. That's just how it works, kind of. It's all the physics and it's all stuff. So there's the same force applied to him in that moment. So this is technically not only the force, it's also the weight, because weight is a force. So we could get the acceleration of the ball and the person. So remember, so W equals mass acceleration. So we need acceleration right now because we have the weight, we have the mass. So we just want to find acceleration. To get the acceleration, we have to divide everything by the mass. So W divided by M, which is now equal to acceleration. So W, 200, divided by 2, that's a 0, equals 100. And the unit for acceleration is meters per second squared. And now for the human, it will be 200 divided by 100, and it equals 2. However, because the force is applied to him, this force, it's not the force that he created, it's the friction. So again, guys, you have to use your brain. If something is the opposite, remember, equal and opposite. The opposite of this number is a negative, so the 2 would be a minus. Meters per second squared. I know it seems very confusing, however, just kind of most of the time, if something is pushed on the right side, so let's say someone pushes them to the right side, that means that the friction, what's on the left, is the friction. Of course, that someone can be pushing the guy also, whatever. However, most of the time, it's going to be like this. Let's say you're in the water, right? You're on a boat, and you throw a ball, right? Again, you apply the force to the ball, and this time, it's more of a, of course, also in the other example, you'd probably move a bit to the left. However, here it's more logical. So you know how in water there's a lot of movement, right? It's all wobbly and all that type of stuff. But it can also be still. So imagine the water is still, right? Then you're not moving yourself, you're moving slightly, literally the most slightest bits. When you throw that ball, the force will go back to you, the friction force, and you will move slightly. It might be literally, slightly, just a couple centimeters or whatever, but that is because of the force you just applied. There's an even better example. So right now we're talking about we're on Earth, right? And on Earth there's everywhere friction. Everywhere is friction. Yes, friction is one that's pushing us, but not at the same time. So let's say, again, we're in the place where there's no friction, space. So here's the moon, here's the Earth. this is, I mean, let's just say it's you. Nah, this, okay, no, let's say Dan. Right? So you have a ball, right? And let's say you want to get back to the earth, right? Dan he wants to go back to the Mother Earth. Where should he throw the ball so he like starts going to the direction of the earth? Where do you think he should throw it? Should he throw it up, down, right, or left? Well, if he throws it up, he will go down because of the force applied to him back. If he applies it to the right, like he throws it to the right, the force applied to him will go to the direction of the earth, and he will probably be home soon. Not soon, but safe.